Alright, so we are talking about we're talking about solvable groups. Don't want to spoil what we're going to be getting to, but let's recall some things. Just because, let's see, it's been a few days since I've uploaded a video, so let's see where we are. We're at, if we have two normal subgroups, A and B and G, then A comma B is a subgroup generated by A, B, A inverse, B inverse, where A is in A and B is in B. So let's see, we have this. Then we have D of group G is just G comma G. And obviously G is normal in itself, so this is well defined. Okay, so G mod, it's DG, which, let's see, we talked about this. This is a commutator subgroup. G mod, its commutator is abelian. And we proved that in one of the previous videos. Okay, so hence, any subgroup of G which contains this commutator, DG, is normal. And why is that? That's by the first isomorphism theorem. So remember, we have a is that true? Okay, so any subgroup of G containing D of G. So we have a one-to-one correspondence between the subgroups of, oh right, because we have a one-to-one correspondence between the subgroups of G which contain DG. Those correspond to subgroups of G mod DG. But subgroups of G mod DG, G mod its commutator is abelian. So any subgroup of an abelian group is normal, just because the abelianity condition, you can move everything around and it's just, everything stays the same. Conjugation doesn't change any elements in an abelian group, and so that's why that's fine. Okay, so every subgroup of here is normal, and therefore, by the isomorphism theorem, every subgroup of here containing the commutator is normal. Okay, so that's that. Conversely, if we have some normal subgroup G and H, is abelian, and this is actually going to be something new, I think. Then D of G is contained in H. And let's see here. So this uses an exercise that was from one of the exercise sets from my class, and I don't think I'm going to get around to doing all those exercises. So let me explain some of these, some of the details in this proof. I'm going to kind of go through an outline and leave some details for you to prove. So to see this, one must first prove that if we have some map phi, which is a group homomorphism from a group G1 to G2, where G2 is abelian, then there exists a unique phi bar, which is a group homomorphism from G1 mod its commutator, and this is going to go into G2, and it's given by phi bar of this coset of so if you have any coset G commutator of G1, it's going to send that to phi of G. So what happens is phi bar, you evaluate at a coset and you end up just evaluating phi at the element G. And part of the proof of this fact is that, okay, so one must prove, and by one I mean you, because I'm not going to go through the proof of this. There should be a proof of this on my channel somewhere. Yeah, go through, watch all the Jacobson videos and click on all the ads, and eventually you'll find it. So, anyways, so we got phi bar defined by this. You have to prove that this is well defined. It turns out it is. Turns out it's also a group homomorphism, and it's also such that this diagram commutes. G2, we're going to go G1 mod the commutator of G1, then here. So we've got phi, we've got projection, phi bar. So basically, going from G1 to G2 through phi is the same as going from G1 to G2 through this path, by going through pi and then through phi bar. And that should be obvious by how, well, if all of this works out, then it should be obvious that that's the case, because phi bar, because you can see phi bar of this, we're evaluating at something that, yeah, you can sort of see that should work out. So anyways, that this commutes. So we say, in this case, phi factors through dg1. And by saying phi factors through dg1 means that we can write phi as the projection onto G1 mod dg1 and then map that into G2. So I guess the factoring means that you're going through this way. I don't know where this terminology comes from, but I guess this is what people call it in algebra. Okay, so then for all G in D, so let's link this back. For all G in DG, phi of G equals phi bar of G dg, which is equal to phi bar of dg. And why is that? That's because if you've got G in here, then yeah, it's just part of this coset, and that's equal to the identity. And thus, dg is contained in H. Right? Do we do that right? Right, because you let phi here be the homomorphism from G1 to G2. You let G1 be the group G, and you let G2 be G mod H, and then phi is given by projection. You just take an element and project it onto the H coset. So really, when I say this, really where we're sending dg is we're sending it to H, because that's the identity element in G mod H. So just to be more clear, that's what's going on here. Okay? Let's see here. So we're going to also recall G is solvable if d to the n G equals the identity for some n greater than some integer n greater than or equal to 0. So here, let's recall that d0, g is just g, and d to the n plus 1 g is d, it's just the commutator of dn g. So you define dn inductively. All right, so that's that. So a solvable group G has a composition series and what you can do is you could just take G and write that as D0G, then it contains D1G, then it contains all the way down to DNG, which is E. Okay, let's see here. All right, yeah, we talked about all this. Each of these DJs are normal in G, and that's something. Let's see here. I have written down here that this is an easy proof. So let's see, why is that an easy proof? Well, certainly. Let's see here. G is normal. The commutator subgroup. We proved already that the commutator subgroup is normal. And then, oh right, so the commutator subgroup of the commutator subgroup of a group is always normal in the group, and so I think we can just induct then, and so dn plus 1 is going to be the commutator of this group, and so dn plus 1 is going to be normal in dn. Let's see here. So if dn plus 1 is normal in dn, then I think you can just use that dn is a subgroup. No. I think you have to be a little bit careful, but it ends up not being a difficult proof. Because if it was a difficult proof, I wouldn't have written down easy proof. So anyway, so that's that. So let's see here. So this is do we here? So we have each dig is normal in G, not just in D I minus 1. So let's write that in G, and each dig mod di plus 1 G is abelian. And again, this is something that we proved last time. So now for the sake of time, I'm going to wait till next time to actually start going into newer material.